So, today we will talk on material balance in gasification. Now, material balance is also an important exercise in order to know the information that is required during gasification. So, normally in material balance, say inputs are say coal, then analysis is to be known. The analysis can be given on wet basis or on dry basis. Then air is used for gasification, then this air can be dry or you can have wet air. So, here one is to be careful. If it is dry air, then the composition of air is 79% nitrogen and 21% oxygen. If it is wet air, that means it is a moist air, then one is to determine the composition of air, because now the air contains, in addition to nitrogen and oxygen, water vapor also. So, another important input is the steam. Normally it is given that so much amount of steam is blown per kg of coal, or it may not be given, depends upon the type of problem and type of gasifier under consideration. So, under this output, what is required to find out, say in the output is say producer gas, normally its composition is given. Now, this composition can be given on dry basis or on wet basis, that depends on the type of problem. Then also amount of tar also analysis is given, and its amount may or may not be given, depends again on the problem. Then output, another is soot, again analysis oblique amount should be known. Then ashes, the ashes is in fact ash plus carbon, again its analysis and amount should be known. Now, here the analysis of producer gas is given on volume percent. In most of the cases, the analysis of gaseous fuel is always given on volume percent unless and until specified, where volume of solid products, it is always given on the weight basis. So, for this given input and output, you are required, you are required to find out, for example, say what is the volume of producer gas. Now, in order to find the volume of producer gas, one has to perform carbon balance. To perform the carbon balance, a carbon from all inputs should be equal to carbon in output, and from that balance one can determine the volume of producer gas. Then also it is also sometimes required to find out volume of air. Volume of air. Now, if air supply is dry, then volume of dry air. If air supply is moist, then volume of moist air. So, in order to find out volume of air, one has to perform nitrogen balance. Now, in performing nitrogen balance, one has to be careful that all sources of input and all sources of output must be considered. Number one. Number two, if the air is dry, then and if the air is moist, then for the moist air one is to recalculate the composition of air depending upon the saturated vapor pressure and relative humidity which will be given in the problem. Then in certain cases it is also required to find out what is the weight of steam that is blown in. Weight of steam that is blown in, and in order to find out weight of steam that is blown in, this amount may be given, but if it is not given, then its weight can be found out. Perform hydrogen balance. Perform hydrogen balance. So, here you have to take into account input of hydrogen from all sources, then output of hydrogen from all sources, and automatically the hydrogen in steam becomes an unknown variable and the amount of steam can be determined from the hydrogen balance. Now, it is also asked, say, what is the percentage H2O blown in or steam blown in that was decomposed. That was decomposed. Now, here one is to perform a sort of a H2O balance, in the sense because all the H2O that is contained in coal, it enters into the producer gas, whereas the steam or the hydrogen of steam, it enters into producer gas, and the H2O of moist air, it also takes part in the decomposition of steam. So, by performing water balance, one can determine what is the percentage of H2O blown in that was decomposed. And last, you are also required to find out, say, what is the percentage calorific value in fuel gas. So, these are the ways, or these are sometimes these are the questions that are being asked, and for that purpose one has to perform the so called elemental balance. Now, let me illustrate by taking a particular problem. Now, in a gasifier, coal of the following composition is used. It is, I am just representing a box just to separate inputs and output. So, on the input side, coal of the following analysis is used for gasification. Say carbon is 79.1%, hydrogen 5.0%, oxygen 6.4%, nitrogen 1.7%, H2O 1.7%, and ash 6.1%, and that makes 100. Now, here air, say let me put this is the coal, and this analysis is on weight percent. Now, another input, let us take it air. So, air is given, air is 80% moist and it is saturated with water vapor at 26 degrees Celsius and 740 millimeter of mercury. That is, the air is moist and it is saturated with water. The temperature of air is 26 degrees Celsius and its pressure is 740 millimeter of mercury, and it is also given that P H2O at saturation at this temperature 26 and 740 millimeter mercury is given to you is 26 millimeter of mercury. Now, in the output, producer gas whose volume is given on volume percent is formed, and its composition is CO2, CO, CH4, H2, N2 and H2O. So, CO2 is 7, CO is 21, CH4 is 2.5, H2 is 14, nitrogen is 53 and H2O is 2.5. Also it is given the Hs. Hs is simply a mixture of H and carbon. So, Hs is 9% of weight of coal that is charged into the gasifier. Now, you are required to find volume of producer gas. One may find, for example, per kg coal, number 1. Number 2, you have to find out volume of air, say moist, at 25 degrees Celsius and 1 atmospheric pressure, also per kg of coal. Third, you are required to find out what is the weight of steam that is blown in. Then you are also required to find out percentage H2O blown in that was decomposed, because mind you, the H2 content in the producer gas is due to the decomposition of steam, and all steam which decomposes, it enters at hydrogen, plus also the steam of moist air, it also enters or it also takes part in the decomposition, whereas the moisture of the coal, it directly enters into the producer gas, because it just evaporates at around 100 degrees Celsius and it enters into the producer gas. Then fifth, you have to find out, say, percentage calorific value of producer gas. So, this is what we have to find out. So, now we take first of all basis. This is very, since here it is already given, you have to find out per kg of coal. So, basis is already clear. So, basis is, say, 1 kg of coal. That is, you are finding out these values per kg of coal. Now, let us consider y kg mole of producer gas. Now, here there is no hard and fast rule that you should consider only kg mole. You can also consider volume. The choice is yours, say in meter cube. So, now if you do the balance, then carbon in coal, that is equal to carbon in producer gas, as you see from the input and output diagram, and plus carbon in Hs, and nowhere carbon is present. So, you have made the balance okay, that is a carbon in the coal, carbon in the producer gas and carbon in Hs. Now, this will be equal to carbon in producer gas Now, remember, the ash is conserved, that is ash of the coal, it enters as the ashes. So, directly this will be, carbon will be equal to 0.09 minus 0.061, that is what the problem says. So, now if you do the kg balance of coal, then we will be getting, say, 1 by 12 0.791 minus 0.09 minus 0.061, because this is in kg. So, converted to kg mole, you have to divide by 12. that will be equal to carbon in producer gas. Now, since producer gas contains CO2, CO and CH4, so volume percent is equal to mole percent. So, I took kg mole. So, directly I can write down the carbon in producer gas, that will be equal to 0.07 plus 0.21 plus 0.025 into y. Now, in this equation the only unknown is y, and it can be solved, and by solution of this equation you will get, say, y. If you solve it, it will come to be 0.208 kg mole. Now, one can transfer it to meter cube, say y, that will be equal to 4.66 meter cube at 1 atmospheric pressure and 273 Kelvin, whereas this value is 5.08 meter cube at 1 atmosphere and 298 Kelvin. So, that is how you can find out the amount of producer gas by making the carbon balance. So, this is the answer for one which is being asked. Now, second asked is the volume of air, that is a moist air. So, second is volume of moist air, or I will put just volume of air. Now, let us consider again x kg mole is moist air. X kg mole is moist air. Naturally, we have to make nitrogen balance. But before nitrogen balance, as I have said, you have to first of all find out the composition of moist air, because 79% nitrogen and 21% oxygen is the composition of dry air. So, for moist air we have to find out in the following way. Say, for example, say we have now PN2 plus PO2 plus PH2O, that is given to us 740 millimeter mercury. Now, say PN2 plus PO2 plus 0.8, which is the humidity, into 26, that is equal to 740 millimeter. So, that if you solve this equation, then this PN2 plus PO2, that is equal to 719.2 millimeter of mercury. Now, again the distribution will be again 79-21. So, the partial pressure of nitrogen in moist air in this present problem 568.168, PO2 151.032, and PH2O, that will be equal to 20.800, and that makes again 740 millimeter. So, from here we can find out, say, 1 kg mole of moist air has the composition, it will have, say, 0.76779 nitrogen, I am writing in terms of fraction, or percent will be 76.779 plus 0.201 fraction oxygen plus 0.0281 H2O. So, this is what the composition of moist air in this particular problem. Now, once you determine this, then nitrogen balance is very easy. Now, the making nitrogen balance, always remember to find out the volume of air, always attempt nitrogen balance, never attempt oxygen balance, because oxygen is reactive and nitrogen is inert. So, making now nitrogen balance, very simple, nitrogen from coal plus nitrogen from air, that is equal to nitrogen in producer gas. Since tar and those things are not given, so it is very simple. So, I am straight away writing nitrogen balance in kg mole. So, that will be equal to 0.017 upon 28 plus 0.76779, that is the into x, which is from air, and that is equal to 0.53 into 0.208, that is in the producer gas. So, now all that you have to solve this equation, it has only one variable. So, the value of x, that is equal to 0.14279 kg mole, that is the answer, and this value will be equal to 3.601 meter cube at 26 degrees Celsius and 740 millimeter of mercury. Because you have to find out the volume of 1 kg mole at 26 degrees Celsius and 740 millimeter, and that 1 kg mole, it comes out to be equal to 25.22 meter cube. You can calculate yourself and convince. Now, this will also be equal to 3.198 meter cube at 0 degree Celsius and 760 millimeter mercury, which is the so called NTP. So, that is how you can calculate the volume of moist air, and in fact, this is the answer for the question which is asked number 2. Now, let us go to the weight of steam. Now, third which is asked, what is the weight of steam, because it is not given. So, as I have said, for weight of steam, you have to do hydrogen balance. So, that is the what you have to do, you have to make hydrogen balance. Now, again on kg mole basis, I am doing on kg mole. So, by performing hydrogen balance, in fact, H in coal plus H in H2O of coal, you have to consider from all sources from where H is entering, plus H in steam plus H in moist air, they are all input, and the output is only single, that is H in producer gas. H in producer gas. So, that is what the balance of hydrogen can make it. Now, this balance I will be writing in kg mole. So, the balance look, that is 0.025 plus 0.00094, I am straight away writing the values, plus 0.00401 plus H in steam, that is unknown. This will be equal to 0.208 into 0.05 plus 0.14 plus 0.025, because the hydrogen in steam in producer gas is in the form of CH4, hydrogen and H2O. So, this is how the hydrogen balance look. Now, here the only unknown is H in steam. So, I can solve this equation and I can find out now H in steam, H in steam, that comes out to be equal to 0.0 1477 kg mole. Now I have to convert it in terms of kg. So weight of steam would be multiply by 18. So that answer will be 0.266 kg per kg of coal. So this is the answer for third one, where it is asked what is the weight of steam. Now fourth, which is asked the percentage H2O blown in that was decomposed. Now here say moisture of coal it enters into producer gas. Say I will do now, say water vapor in gas producer, say water vapor in producer gas, that is equal to water from evaporation of coal plus water as undecomposed steam. Because the steam which does not decompose, it directly enters into the producer gas. So by doing the water vapor balance, one can determine the undecomposed steam, and from the total steam we subtract it, we get the steam which is decomposed. So if I do this balance and write it, say for example 0.025 into 0.208, that is equal to 0.017 upon 18, plus if I consider Z moles of water which are undecomposed, then I can find out the value of Z, that is equal to 0.004255 kg mole undecomposed. So steam decomposed will be that will be equal to 0.266 minus 0.004255. So now here itself, if you want to know in kg, multiply by 18. So the answer will be 0.1895 kg steam which is decomposed. So percentage of steam blown in that was decomposed simply decompose upon total into 100. So that answer is 71.2%. So that is the answer for fourth one. Now we have to find out calorific value to determine calorific value of producer gas. Now the determination of calorific value we have done on several occasions in the earlier lectures also. So all that you have to find out the combustible component of the producer gas, find out their kg moles, multiply by their respective heat of combustion, add them together, and you will be getting the calorific value of producer gas. I do not enter into those detailed calculation that you can do yourself. So the calorific value of producer gas that we will be getting is 5.64 into 10 to the power 3 kilocalorie. Now, if you are interested in finding out what is the fraction of calorific value of coal that is present in producer gas, then you have to find out, say, NCV of coal. Net calorific value of coal, again by Dulong formula, and this comes out to be equal to 7566.32 kilocalorie per kg. Now, here fraction, to find out the fraction. So, the fraction of CV of coal, that is available in producer gas, that is comes out to be equal to 74.54%. Now, here it is also important to know what happened. That means, you are unable to find 25.46 percentage of calorific value of coal is lost. That is, this analysis is very important. Now, these losses, they can be of several nature. One loss could be, so, sensible heat of gas, because producer gas is discharged at some temperature, so it will also carry sensible heat, and second loss could be heat losses. So, this thing will help you to locate and take effective measure in order to conserve the heat. So, that is how you will be performing the so called material balance. Now, for your practice, I am giving you one more problem that you can solve yourself, and the problem is as follows. So, I am giving you an unsolved problem, and this unsolved problem I have taken from the book R. Schumann, Metallurgical Engineering Principles. So, the problem is as follows. In a gas producer, coal of composition is on dry basis and given in wet percent. Say carbon 83.9, hydrogen 5.0, sulfur 0.7, nitrogen 1.4, O 1.7, and the ash is 8.3, all in percent. A is for ash. Now, this coal is gasified and the following products are obtained. And the following products are obtained. So, tar, soot and ashes. The analysis is given, ultimate analysis, dry basis and given in wet percent of all the three products. Tar analysis, carbon 62.5, hydrogen 4. Now, mind here given percent sulfur plus oxygen plus nitrogen, that is equal to 21, and ash is 12.5. Soot, carbon 92, ash 8, ashes, carbon 4.9, sulfur 0.4 and ash 94.7%. Producer gas composition on volume percent and on dry basis. It is given CO 26.7, CH4 3.5, hydrogen 13.9, CO2 4.3 and nitrogen 51.6. The problem continues on the next page. Say coal as fed contains 2% moisture. Air is dry. The amounts of tar and soot are 55 kg and 40 kg respectively per 1000 kg coal. Steam was fed at 0.35 kg per kg of dry coal. Now, in the problem we are referring only the dry coal because the analysis is given on the dry basis. So, what you are required? You are required to calculate, say calculate net calorific value of tar and soot. Now, mind you, in calculating the net calorific value of the tar, in the tar the composition N plus O plus S is total is given. So, we have to find out first of all the O content of tar according to the proper balances. So, I am giving straight away the answer to you so that you can solve. So, the NCV of tar is 6493.8 kilocalorie per kg and that of soot is 7452 kilocalorie per kg. This is the answer. Now, second you have to find out meter cube of dry air and the answer for this is 2.818 meter cube per kg dry coal. Third, find out meter cube of producer gas. And the answer for meter cube of producer gas, answer is 4.134 meter cube per kg coal. Then you find out percentage H2O in producer gas. Answer 3.5%. Then you find out percentage steam blown in that was decomposed, and the answer for this is 62.79%. Now, mind you, here you have to do the proper balance in order to find out the various things which has been asked over here. Example I had already given. So, you have to perform it, you have to find out the weight of ashes, then I can do carbon balance, hydrogen balance, nitrogen balance, oxygen balance and so on. I think you should be able to do it. Now, next which I want to illustrate a little bit about the heat balance, as I have said, that is heat consumed for decomposition of steam. that should be equal to heat produced by the gasification reaction. So, if you do a simple problem, so the problem on say heat balance, say in a producer a mixture of air, pure carbon and steam is gasified, so that the gasification reaction go to completion and the product contains CO, H2 and nitrogen. Reactants enter at 25 degrees Celsius and products leave at 25 degrees Celsius. The gasifier, it operates under adiabatic condition. Now, for this ideal adiabatic gasifier, you calculate steam rate, that is kg per kg of carbon, you calculate gas yield in meter cube per kg of carbon, then gas analysis, and then calorific value of producer gas or of gas which is being made, calorific value of gas, that is what you have to calculate. This gasifier uses air for gasification. So, very simple, the gasification reaction we have to write down. So, the gasification reactions are the solution, gasification reactions are C plus half O2 plus 3.76 N2, that is equal to CO plus 1.88 N2. Number 1. Number 2, C plus H2O, that is equal to CO plus H2. So, reaction 1 is exothermic, reaction 2 is endothermic. So, now if you consider say 1 kg mole of carbon, 1 kg mole carbon that is available to us, and let us say x kg mole carbon is used in reaction 1, then 1 minus x kg mole of carbon will be left for reaction number 2. So, if you write down those reactions again, say xc plus x by 2 O2 plus 3.76 N2, that will be equal to xco plus 1.88 x N2. This is reaction number 3. Now, then 1 minus x C plus 1 minus x H2O, that will be equal to 1 minus x CO plus 1 minus x. So, that is what the reaction is there. Now, by doing the heat balance, say heat produced by equation 1, that will be equal to heat produced by equation 2, or more precisely in terms of moles that we use x kg mole, then heat will be produced by 3 and heat will be consumed by 4. So, if we write down the heat of combustion values I had already given on several occasions. So, I am straight away writing from here the heat balance. The heat balance will come out to be equal to say 29.6 into 10 to the power 3 x, that is I write here heat balance, that will be the heat produced by consumption of x kg mole in reaction 3, and that will be equal to 1 minus x into 10 to the power 3 minus 29.6 plus 57.8, that is the heat consumed by reaction 4. So, I solve this equation, I will be getting the value of x, that is equal to 0.488 kg mole. So, what I do now? I rewrite these equations 3 and 4 and straight away I can calculate the questions which have been asked. I am straight away calculating. I will write the equation for you. So, the equation now C plus 0.244 O2 plus 3.76 N2 plus 0.512 H2O, that will be equal to CO plus 0.917 nitrogen plus 0.512 H2. Now it is straight away. So, steam rate will be simply 0.512 into 18 divided by 12. So, this answer will be 0.768 kg per kg carbon. Gas yield 1 plus 0.917 plus 0.512 multiplied by 22.4. So, gas yield will be equal to 4.53 meter cube per kg carbon. Now, gas analysis, simply 41.1% CO, 37.75% nitrogen and 21% is the hydrogen. Now, you can find out calorific value. It has been done on several occasions in per meter cube. That will come out to be equal to 1880 kilocalorie per meter cube. So, that is the answers along with the solution for that particular problem. Now, I will request you to do this problem and repeat the calculation on steam rate, gas yield, gas analysis when gasification is done with pure oxygen. So, I repeat once again, for the same adiabatic operation of the gasifier, the only difference now is that the gasifier is operated now using pure oxygen. Earlier it was operated with air, now I am operating with pure oxygen, rest all are same. So, you have to calculate again steam rate, to calculate gas yield, calculate gas analysis and calculate calorific value again kilocalorie per meter cube. So, if I thought I will not give you the answer, but well, answer I should give, because steam rate will be the same as it was earlier. The gas yield, now the answer would be equal to 2.82 meter cube per kg carbon. This is the answer. Steam rate is same as 0.768 kg per kg carbon. Gas analysis would be 66.14% CO and 33.86% hydrogen, and its calorific value per meter cube is 3021 kilocalorie per meter cube. So, you are seeing now, if you operate the gasifier with pure oxygen, then the calorific value of the producer gas, it increases by a factor of, say earlier it was 1880, now it is 3021, is of the order of, I will say of the order 1.6 times, and that is what the advantage of gasification with oxygen.